This is the third time you're going to hear about VeriPB, so I can again run through even fewer details than the previous speakers have, because you're all experts in VeriPB now. So we are using a proof system for pseudo-Boolean constraints, and we have a verifier program that can verify proofs written in this system. And the proof rules are based upon cutting planes. Now, for me, I'm going to make use of another proof rule that hasn't been mentioned yet, but it's really just a kind of syntactic sugar for a set of cutting plane steps. This is the reverse unit propagation rule. I've put unit propagation in big scare quotes because this is obviously a generalization of unit propagation to the pseudo-Boolean setting. So it's not entirely involving units, but essentially we can introduce a clause I should say a pseudo-Boolean constraint if the negation of that constraint unit propagates in this generalized sense to contradiction on our formula. And then we have more rules. We've heard about the redundance rule. I'm going to just use this in the sense of an extension rule like we heard this morning. So we can introduce fresh reified variables. So I don't need the full power of that, but I can use it to implement this extension rule. And we have dominance deletion rules that you've heard about. I'm not going to make use of that in this talk, although it is interesting, obviously. And we have all these applications for VeriPB, some of which you've heard about: proof logging for MaxSat, certified symmetry breaking. There's also other things which you haven't heard about. We can certify graph algorithms using VeriPB. We can do certified CNF translations. I think we heard a little bit about that. Certified parity reasoning. So there's lots of things that can be done with this proof system, and kind of the question arises, can constraint solving get in on this party? And I'm going to argue the answer is yes. So what do we need for a proof logging system for constraint programming? Well, first of all, we want something that's going to be simple for solver authors to implement, and also expressive enough to capture the kind of reasoning that we do in constraint solving. So I'm going to focus on the two big things that kind of make a constraint solver a constraint solver. We're backed fundamentally by a backtracking search procedure, and then we take advantage of these specialized propagation algorithms. So you'll think back to Kieran's talk yesterday on how they work. So let's start with the kind of the easy bit. This is going to be relatively straightforward. How can we proof log backtracking search, making use of the cutting planes or this reverse unit propagation rule in a pseudo-Boolean setting? So we're making guesses, and then we're hitting a contradiction, and then we're backtracking. And what we're going to do to produce a proof of this is anytime we backtrack, we're going to output the negation of the series of guesses that led us to want to backtrack. And we're going to continue doing this. And we're going to say this follows by reverse unit propagation because we contradicted something. So at least one of these guesses can't hold. So that's what that says. And we continue to do this for every single backtrack until eventually we're going to backtrack from the first variable that we decided to branch on. And we're going to have eliminated both values. We're going to say it can't be 1, it can't be 0. And so the problem as a whole is unsatisfiable. And that gives us a complete, providing we log all of these reverse unit propagation steps in the same order that we solve them in our backtracking algorithm. This is going to give us a complete proof of the procedure. So that's really straightforward. And at the core of a constraint solving algorithm is also a backtracking algorithm. So we'd like to say for our solver authors, anytime you backtrack, we want you to output a RUP statement that is the negation of the series of guesses up to that point in the solver. And that should be quite straightforward. Of course, this is pseudo-Boolean proof logging that's been talked about so far. And I'm suddenly telling you I want to apply the pseudo-Boolean proof logging to constraint solving. So pseudo-Boolean, we're obviously dealing with 0, 1 variables. Constraint solving, we can have these multi-valued variables with much larger domains. So we're going to have to think about encoding the problem in some way. And the kind of key point to think about here is we're still using our original solver. So we're not encoding the problem in the sense of Marine's talk and then solving that encoded problem. We're somehow just using the encoding for the proof. So in this sense, we don't need the propagation strength of our encoding to be particularly smart or good. We just need the encoding to be quite obviously correct. So we understand quite well how to encode CP problems to SAT and therefore to pseudo-Boolean. There's some very obvious encodings we can use. There's the direct encoding, which we introduce PB variable for each possible domain value, and then we enforce a constraint saying exactly one of these needs to be true, and that's our PB variable domain constraint for the CP variable, and we do this for all the variables in our problem. That's fine, except we need a single variable for every domain value, and we could potentially have a very large domain. We could have from -1,000 to 1,000, and that would be, well, 2,000 variables in our PB model, which wouldn't be ideal. So we can take advantage of a more compact encoding, which doesn't have necessarily as great propagation strength, but we encode instead the bit value or the value represented as a sequence of bits. So we have enough bits to cover this whole domain, and then we constrain that the 2's complement representation of these bits falls in the range that our domain is representing. And that's obviously using a logarithmic number of variables, and it's going to save us a lot, and also might make it easier for us to encode certain CP constraints. But in general as well, like if I said before, we're going to have this sequence of guesses, we might want the direct encoding as well. So it's kind of a toss-up to think which one should we choose. And the good news is we can somewhat have our cake and eat it here. We can use the logarithmic encoding and then introduce the bits of the direct encoding on the fly as and when we need it, using the proof rules and using some reified constraints. So we can reify pseudo-Boolean constraints. This is pretty straightforward. So like this is really just a shorthand for obviously 2 constraints, 2 implication constraints either way. And this in turn is just a shorthand for putting a large enough coefficient on the first value in the PB constraint so that the rest of the constraint is either turned on or off as you would want it. And this, in vanilla pseudo-Boolean terms, gives you exactly the logical implication that you would want. But we can just kind of hide that behind, again, some syntactic sugar and say that we're introducing a double reified pseudo-Boolean constraint here. So if we want to introduce the direct encoding on the fly, what we will do is we will have, so say we want to introduce x equals 3 as a direct variable using the 2's complement encoding as our base encoding. We introduce x is greater than or equal to 3. Then x is greater than or equal to 4. And then we make sure that x is greater than or equal to 4. We'll propagate x is greater than or equal to 3. We need this when we're excluding all the domain values at the end. And finally, we introduce x equal to 3 as saying greater than 3 and not greater than or equal to 4. Sorry, greater than or equal to 3 and not greater than or equal to 4. So that's how we get kind of both encodings as and when we want them. And we can introduce these in our model of the problem, in our pseudo-Boolean model, or we can introduce them in the proof as and when we need them using the redundance or the extension rule as I'm using it. So that's all possible. So when we've got this encoding of variables, we can always just pick the kind of most straightforward encoding of constraints that we can think of. So it's very straightforward to do this. If we had, say, a linear inequality constraint, we just multiply up the bit encodings by the relevant coefficients, and this gives you the same CP constraint in pseudo-Boolean form. We have an equality constraint. We can do this as 2 inequalities, again, pseudo-Boolean. And if we have not equal, we can use the reification. One of these auxiliary variables we introduce, f or not f, must be true. And this is just saying a is greater than b or a is strictly less than b. And again, that's a not equals constraint. But these are not the kind of constraints that CP is famous for. It's these kind of more expressive global constraints that kind of makes CP a useful paradigm. So you heard a lot yesterday about the all different constraints. And we can decompose this down if we want into a clique of not equals constraints. A better way to do it, it turns out, for our proof logging purposes is to encode it like this. So this is just saying at most one between these variables can take each of the possible values. And we have to introduce these equals variables if we're using the log encoding. And this gives us a way to encode all difference. And we can proceed through all known CP constraints in this way, taking well-known encodings, going for the simplest encoding where possible, because we don't necessarily care about the propagation strength. So once we've done that, we can now tell our solver authors, hey, you can backtrack and you can proof log by introducing or just asking for these equals variables and then encoding your sequence of guesses. I've used OR notation there. This is obviously just plus greater than or equal to 1 every time we backtrack, and you work through. And introduce a RUP statement every time you do that. And that is going to give you, just like in the small PB example, this is going to give you a complete proof of a backtracking procedure for CP, which is nice and great. Of course, CP would not be interesting if all it was a backtracking procedure. And all of the kind of strength comes from these specialized propagation algorithms. So what we're going to say is, this is going to be the skeleton, if you like, of our proof, but we're going to have extra steps in here which justify the propagation, any inferences that are made by propagation algorithms. So anytime we reverse unit propagate these backtrack clauses, we're going to maintain the invariant that anything that was known to the CP solver at that point is available through reverse unit propagation of the backtrack clause at that point. And therefore, this proof skeleton will remain valid even when we've cut off parts of the tree via the smarter CP reasoning. So this is what we're going to focus on now. If we're going to try and maintain this invariant, how can we actually do proof logging for these specialized propagators? And this is where the cutting planes reasoning, there's kind of a point in using it because we found that there's actually some really nice ways to proof log these specialized propagators that might not have been possible in another proof system. So sticking with the all different, as it's kind of the canonical example, you'll remember, if you were there from Kieran's talk yesterday, how the propagator for all different works. It represents the variables and domains involved in the constraint as a bipartite graph with edges for which values are still involved in each variable's domain. And I'm going to just focus on the case here where the all different propagator decides in advance that we can backtrack early. So in this case, it's pretty obvious. We've only got 2 values between these 3 variables. So even though we haven't assigned all the variables yet, we should be able to turn around and say, okay, we're going to backtrack early here because this is obviously not satisfiable. So at this point, our proof skeleton that we had before isn't going to allow us to just deduce this on reverse unit propagation. We're going to have to add some extra steps so that that contradiction remains valid when we have that series of guesses. So we're going to have to take a look at what the all different propagator actually does and then see what steps we can log as a result of that in order to get our valid reasoning. So you'll remember from yesterday, the all different constraint is satisfiable if and only if a maximum cardinality matching is left saturating. So turning that the other way around, it's going to be not satisfiable if we have a maximum cardinality matching that is not left saturating. And this is called a Hall violator. It's basically just we have 3 variables with 2 values between them, or n variables in general with fewer than n values between them. This is the thing that tells you that this is not possible. And although the all different propagator doesn't necessarily produce this Hall violator, by default, it's very easy to modify any standard all different propagator to get this Hall violator out as a kind of byproduct of the algorithm, which turns out to be really useful because we can use this to output proof steps in cutting planes. So the kind of smallest example we can come up with that's actually sort of interesting is on 5 variables, 5 values. I'll show you what this looks like. So imagine we've got this situation here. We've already made some derivations, and we're going to assume that we've maintained this invariant thus far, that everything that is already known to the solver is available on unit propagation of any backtrack clause. So this is what we know already. We know v is less than or equal to 2, et cetera, and that's what's shown in this bipartite graph. So the all different constraint then looks at this. In fact, a human can look at this quite easily and say, okay, these 4 values here, none of them connect to the values 4 or 5. So this is going to be a Hall violator because these are 4 variables with only 3 values between them. And the all different propagator will notice this and say, okay, contradict, we can backtrack here. The proof needs some help. And so we'll use this Hall violator to do the following. So first of all, what we'll do is we'll introduce these RUP statements, which are really obviously implied by our direct encoding. In fact, if we were using the direct encoding, these would be here already because they're just saying that each variable needs to take at least 1 value. And we can reverse unit propagate them in if we've been introducing this direct encoding on the fly. And we'll also have in the model, like I said earlier, our encoding of the all different constraint, which will say at most 1 variable can take each of these values, which are the 3 values involved in our Hall violator here. So we have these, and obviously we'll have these for 4 and 5 as well, but we'll pay attention to these three, which we can access earlier in the proof, and these four. And using the power of cutting planes, we have the power to add. So we will add all of these things up, and lots of things are going to cancel out. So in particular, all these equal to 1 things at the top will contradict with, not contradict, cancel out with the equal to 1 things here. These ones will cancel with these ones. These ones will cancel with these ones. And we'll eventually get this down here, which is all the things left over. Now, this is a constraint that we've derived via sound cutting planes rules. And then later on, when we're backtracking, or immediately when we're backtracking, this will actually allow us to contradict now in our proof based on the reasoning performed by the all different propagator, because we already know all of these things. So we're assuming by our invariant that these are all available on reverse unit propagation of the backtrack, which means in particular, because we know that the values 4 and 5 were not involved in our Hall set, all of these are going to be 0. So we're going to be left with something that's always going to be unsatisfiable. In this case, it's going to be, no matter how you set these variables, the most that they could be is 0. So they're never going to be greater than or equal to 1. So this is going to give you a contradicting clause. And obviously, this is just one example, but you can generalize from this example that this will always work. If you have a Hall violator and you add up these constraints in this way, you're always going to get something that allows you to contradict. Yes?
You're trying to prove. Okay, I'll get. So it looks like you're trying to kind of guess a proof of pigeonhole, right? So here you have a pigeonhole problem, and you say it's very easy to adapt and get a contradiction. So is it always easy to reprove a pigeonhole?
So we're using the fact they're all different propagator. So in constraint satisfaction, this is kind of what Kieran was saying yesterday, pigeonholes are easy for constraint solvers, although they're difficult for SAT. Now, because we already know this Hall set because of our constraint propagator, if we had to find this within our pseudo-Boolean setting, that would obviously be a difficult problem. But because we have it from the constraint solver, we're able to just output this in our cutting plane step and prove.
So you think knowing that there is a pigeonhole there, okay, Hall set that all diff generates, you can produce these constraints and the derivation that gives you proof.
Yeah, so we keep track in the solver of which line numbers corresponds to each of these variable values, and then we just output this whenever they all different constraint. And there's a polynomial algorithm for identifying these things. So that's kind of what helps us out here in terms of proving this. So yeah, this gives us a proof for pigeons, and this is kind of why we think that cutting planes or very PB proof system over potentially other proof systems might be the way to go here. Amongst also, this is going to be easy for solver authors to output because these are relatively simple statements in contrast to having to find all these cutting planes steps yourself or find something in another proof system. And this was obviously just one propagator. There are many propagation algorithms for many different constraints. And so far, the good news is that lots of the commonly used constraints in CP have similarly nice or even easier ways of proof logging them using simple cutting plane steps and reverse unit propagation. So these are all the ones that are done so far. These are all implemented in a prototype constraint solver at Glasgow that we've shown basically that these work and that these are good. Obviously, this is, so basically I'm going to kind of end the talk here with sort of various kind of open questions that is kind of what I'd like to sort of look at kind of going forward. So obviously we've got these ones and this is great and this works. There are a lot of CP propagation algorithms. I think there's more than 400 is the number that keeps getting thrown around. So kind of my first open question is, this was very nice for these kind of core constraints that we definitely want to use. Is this going to be very nice for everything? And the hypothesis scientifically is yes, that we think very PB cutting planes, this kind of sits in the area where it's expressive enough to get everything that we want, but also simple enough that it's simple to verify. So we're hoping that it operates inside that zone, and indeed we believe that it does. We just need to go ahead and do this for all these constraints. Kind of second question is to do with the encoding. So I said before, we don't really care about the propagation strength of our encoding because we're just using them within the proof and not to actually search for proofs in and of themselves. However, what smarter encodings will give us is shorter proofs, because if more things follow on unit propagation, then we don't need to do so many steps in order for the reverse unit propagation of the backtrack clause to hold. And there has been some work done where certain encodings in CNF of CP constraints on unit propagation give you generalized arc consistency, and so do the same reasoning that the CP solver would do. We know we can't do this for all things, so we can't do it for all different, but it does kind of emit this question of, if there does exist a better encoding, should we be using it? And indeed, if we're getting a shorter proof, is that necessarily what we want? So we have a proof trimming, a kind of prototypical proof trimming for these kind of proofs at Glasgow. One of the things we're noticing is that short proofs aren't always necessarily faster to verify. So somehow these extra constraints that seem kind of redundant are eliminating things when you're reverse unit propagating and actually allowing you to verify faster. So this is kind of a question. And I suppose the other side of this as well is, if we're using a smart encoding where it's maybe not quite so obvious that it really does represent the original problem, it maybe seems perhaps less legitimate if we're talking from a verification point of view, because this part of the process isn't yet formally verified. I said this, what is an encoding anyway? What I really mean is, I've had this discussion literally just before the talk, is what do we want from an encoding where we're using that encoding to log our proof? So just saying that there's a bijection between the solution sets isn't going to necessarily be enough, because I can present an encoding of an unsatisfiable problem that is just the PB constraint that says false, and then I present an empty proof, and this is going to be a valid proof somehow of that false PB formula. But it's kind of hard to argue that that's a valid proof of our original CP problem, unless we've encoded it very carefully so that each CP constraint really does map to a certain set of PB constraints, and each CP variable maps to a certain set of PB variables. So that's kind of a tricky thing to formalize. There's some definitions I've seen before which talk about this, the equivalence of constraint satisfaction problems, in more than a sense of just the solutions are bijective. This paper here still doesn't quite give us what we want, because it still defines equivalence of all unsatisfiable problems, but it's maybe getting towards what we might want. So this is something to think about. So yeah, I've changed this to say what is a proof-preserving encoding anyway, at the request of Oz. So, and yeah, that's the same slide. So another thing that's kind of been a little bit irritating and would be interesting if anyone has any theoretical insights on this is, we're often relying on things that unit propagate in our encoding. So we've used this log encoding, and we want to say, okay, we have activated these constraints and all these bit values are going to be set correctly. And it's kind of clear to say that that is going to work. Is it going to unit propagate? I mean, you can look at it, and we've been doing this several times where we say, well, it's kind of going to bounce between the upper and lower bounds until we get exactly what we want. Proving this is an inductive argument. It is true. I have a document where I proved this in excruciating detail, and it's kind of not very interesting, but it's what I would like to say is there something about how constrained these encodings are when we can say structurally over these, what is going to unit propagate without having to actually go in and say exactly what these unit propagation steps are going to be in every case. This might be an undecidable problem or an unsolved problem, or it might be something that's already been solved in a different domain, and I just don't quite know how to map it over to this setting. So this is something that I'd be interested to hear about. Is there something structural we can identify here that will save paper and trees or PDF space, I guess. This is the last one's a bit of a silly one, but it was pointed out to me before that people are quite used to RUP as a concept from SAT, and in unit propagation from SAT. We're now using RUP in the pseudo-Boolean context, and the name's kind of a little bit not ideal anymore, because we're not really, like I said, we're not really talking about units. So I would like to maintain this acronym RUP, because it's all over the literature, but to get it to stand for something else. So if anyone can encapsulate this generalized notion of unit propagation on pseudo-Boolean constraints, but still get it to stand for RUP, that would be excellent. And please tell me. I did ask ChatGPT because of course you do, and it's rubbish. So like we can clearly do better than this. We can come up with a better acronym for RUP. My best idea would be refuted under propagation or reverse refuted under propagation. Or anyway, okay, that's the end of my talk. So any questions or answers to my questions would be much appreciated.
Let's begin with you that will sit here.
Yeah.
Any questions for Matthew? Yeah.
Yes, I guess I have a little bit more high-level question. So Jeremy just presented proof logging for Maxat, and he was saying that solver can give you a correct answer, but reasoning is incorrect. So I'm just trying to position your work. So when you run all different propagator, it does a lot of things. It maybe doesn't find whole set immediately. So you're verifying the results, or you're verifying the execution of that every step the propagator is doing is correct.
So we're requiring that every propagation algorithm has to justify its own reasoning, basically. So we're not just proving a particular result, we're proving that this result follows in the way the solver solved it. So by this particular backtracking of propagation. So yes, I would say we are proof logging the process as well.
But inside the propagator, you're like not all different propagators explicitly giving you a whole set, or like you can have a flow-based propagator or something like that. But in the end, you have a particular way that you output. So you kind of have a byproduct of the filtering algorithm that justifies the pruning or proving that there is no solution. So right, so you're more like verifying the result of the propagation algorithm rather than every step what the propagation algorithm is doing.
So in a sense, yes, each propagation step is the step that gets proof logged, not necessarily every individual thing that the propagator did in order to do that step. But if we substituted the all different propagator for a different all different propagator, for example, we'd have to potentially proof log it differently. So if we just decomposed it into not equals constraints, we would use the way of propagating not equals for that rather, like we wouldn't still output a whole set for it because it wouldn't produce that as part of the propagation process. So yeah, so it's each propagation step, which can happen multiple times at each node in the backtracking, is the step that we want to proof log. And we might do it with several statements or just one statement, depending on. So some propagation steps follow by just one RUP statement is all you need. So table constraints are like this, or several RUP statements rather than cutting plain steps.
Thanks. Close.
Yeah, we'll go easy on you. Yeah, so I have a question. I'm curious how you decided which constraint propagators to go after first.
So I personally did not start this process, but I think essentially it's the ones that you would most want. We're kind of doing it in that sense. So we're starting with, okay, what is the absolute minimal set of constraints that you would want and to be able to call it like a reasonable constraint solver. So that's kind of where this set of like basic constraints came from. Not so much these three at the bottom, they're kind of extras, like nicer ones, but like these first few are like the core constraints of any constraint solver worth anything should probably be able to support some version of these. And then obviously when you get into more specialized applications, you're talking about scheduling problems or you're talking about something else, there's more specialized constraints. So we were kind of working from the core outwards, I guess, into different fields. So I wouldn't say we started with the constraints that are necessarily the most easy to proof log, although that might turn out to be the case. Hope that answers the question.
So how long will it take to put these 400?
Well, so we've done Smart Table, and Smart Table allows you to, a lot of other constraints like lexicographic constraints can be basically represented as a Smart Table constraint. So hard to say. When I wrote my research proposal, I said I was going to do 3 in my PhD. I've done 3. So maybe over a year, that would take me to 12 by the end of my PhD. But hopefully, as we do more constraints, it'll kind of knock off chunks of these rather than doing one at a time. So maybe by the end of these 4 years, we'll have them all. That would be nice. That's certainly the hope.
All right. Thank you very much.
Thank you.
And